Here we have Dr. Christine Smit from NASA. This is another talk for the Earth, Ocean, Geo, and Atmospheric Sciences track. Christine is a software engineer at NASA Goddard Earth Sciences Data and Information Services Center. That's a long name. And she's going to be presenting on free, public, standardized Zarr stores of geospatial data in the cloud for all. So go for it, Christine.
Thank you. Can you? Thank you. So my name's Christine. I'm from, we could just call it the Jez Disk, it's a lot faster. It is one of NASA's 12 Earth Science data archives. So there's a whole long list of people who were involved in doing this presentation, some of whom are in the row over there. So this is not just my work, this is work from a whole bunch of us. So I'm gonna go over like a little history about how we ended up making these Zarr stores public. I'm gonna talk about the data. I'm gonna do a demo. I'm gonna talk about where you can get some documentation on how to access this data. I'm gonna talk about some limitations of the data as we have released it, our future plans, and how to contact us. So we're gonna do like a little side trip here, and I'm gonna talk about a tool called Giovanni. So Giovanni is a tool that we've had at the Jez Disk for more than 20 years. It allows you to run some simple statistics and plot them for about 2,000 data parameters in a browser. So you don't have to download anything, you don't have to write any code. Everyone here loves code, but not everyone does. And you don't have to deal with trying to figure out data formats or how you're going to open this thing. So on the tool building end, what this meant was that we had to be able to write code that could calculate these statistics across a wide variety of data products. And if you have ever come to NASA and looked at our data, you will see that there's a wide variety of metadata in those products. So what we did in order to simplify these algorithms so we didn't have to like keep saying, okay, this is how you find time for this product, this is how you find time for this product, is we actually normalized that data as it came in so that our algorithms could be a lot simpler. So what I'm showing here are screenshots from our current on-premises system, which is run on like one big beefy server at NASA Goddard. So we started getting some funding to investigate moving this system into the cloud in about 2018. And so we knew that one of our primary decisions was going to have to be around the data format, how we were going to put this data in the cloud, because we knew that at the time the traditional HDF and NetCDF file format was not going to work well and be very performant in the cloud. So when we were looking around, we found Parquet. There weren't like a huge number of options around at the time that were popular. So we spent several years kind of building out a system that was based on Parquet. Now, I think a lot of people in this room are perhaps more familiar with Parquet and that kind of file format maybe than some of how NASA organizes data. So our data, generally speaking, are these kind of multi-dimensional arrays, which is common in Earth science, where you have maybe a latitude dimension, a longitude dimension, and a time dimension. So you can imagine this sort of enormous cube of data. But Parquet is a columnar file format, and so we had to figure out how to take those multi-dimensional arrays and kind of stick them in a giant table. And so we did what lots of people do. We basically turned it into point data. So, and I do want you to look at these dates, right? So we're talking now several years ago. When we did this at the time, the good thing was with Parquet that the algorithm writing was just like ridiculously easy. It was just like an SQL query and you're done. So we ended up with a very nice, clean, simple architecture, which all of us love. And at the time, when we looked into open source solutions for the tasks that we were trying to achieve, at the time, they didn't perform particularly well. So we ended up going with AWS Athena, which is an AWS service that can read Parquet files. And for the most part, its performance was actually very good, except when it wasn't. And it was just sort of inconsistent and hard for us to know when it was going to work and when it wasn't. And then the thing that sort of really killed it was we knew that there were going to be some looming cost problems. So AWS Athena can be quite expensive. For some of the algorithms that we knew we were going to have to run, we knew that it was going to be expensive to run them on AWS Athena. And then the other issue was that our data sets, for the most part, are updating, right? The satellite continues to go around the Earth. We continue to download data. We continue to update our data set. And so if you've created like a terabyte Parquet file or multi-terabyte Parquet file, and you need to add like a few more rows of data and then upload that thing, I mean, it's not fun. So if you're interested, I did actually give a talk about this in 2020 at SciPy, and I have that link at the bottom here. So we're sitting there, it's 2020, and we're like, okay, like we've kind of gone as far as we can go right now with Parquet. What else is there? And we found Zarr at SciPy, in fact. So starting in 2020, we began looking at Zarr. And the good thing was that it supported multidimensional arrays natively. So it was just like very compatible with the NetCDF and HDF data models that we were very used to. And so it was just a very good fit for our data. It is easy to update as new observations come in. So if you are familiar with Zarr, every chunk in a Zarr store is stored in its own object. So when you are updating that Zarr store, you only need to write those chunks that are actually getting updated. You don't have to write the whole thing. And then, you know, it has really excellent open source support. So the sort of the only thing that sort of caused us some headaches is that, you know, you have this reader and writer problem. So if you throw all of your data in one object, then the thing that's reading it either gets the old version or it gets the new version, and it's never going to get something in the middle. But because Zarr, you know, writes to all these different objects, you have that problem that you could like get half of the old data and half of the new data, and it could be kind of a mess. So we have an internal solution to that, but it's not something that works for making those Zarr stores public. And so as a result, what we're making public are 24 complete Zarr stores. So there's no new data coming in. You folks can access this data, and there shouldn't be any problems. So all of these 24 variables are from a GeoDAS product. This is land surface model data. It is 3 hourly temporal resolution. It is quarter degree. It has a global spatial extent. It is land only, and it has a nice long temporal record from 1948 until 2014. So I've used some terms here that if you haven't dealt with NASA's data are maybe unfamiliar with you, so I'm just going to take 2 seconds to talk about that. So we talk a lot about products, sometimes known as collections, and these are just a group of files that for some reason we call granules. So if you look at each of these individual granules in this GeoDAS product, there's like a whole bunch of measurements within each file. So I think the image I want you to have, like the reason why the data looks like that, is that, you know, the satellite goes around the Earth a few times, we download some data, we run our algorithms, we get these measurements, we create a file, we archive it. The satellite goes around the Earth a few more times, we download that data, we create a file. That's how we build this archive, and that's why we have like tons and tons of files that each only have like, say, one timestamp in them. Okay. So if I were to open one of these granules in that GeoDAS product, this is kind of what it would look like. You would see that there'd just be one time slice. There'd be some coordinates, which is, you know, always good to know where and when the data is. There's bounds for one of these coordinates and not the others. There are 36 data variables in here, so a whole bunch of different kinds of measurements. And then at the global level, the attributes give you some metadata about this particular granule and the product in general. Now, the reason I went through this whole discussion of Giovanni, which you've now forgotten because it was like 10 minutes ago, is this, normalization. So the primary reason for us to have a Zarr store is actually to serve these algorithms in Giovanni. And so as a result, when we pull that data in, we don't just leave it the way it was. We actually do some pretty aggressive normalization. So the first thing we do is that we standardize the dimensions and the bounds. So we standardize the name of those dimensions, we standardize the order, we standardize the units so that our algorithms don't have to muck with any of that stuff. And then we aggregate the whole thing across time. So you get one object for the whole collection. But we only include one measurement in each Zarr store. So rather than you opening it up and seeing like 36 different things, you're going to open it up and you're going to see one thing. So if you are familiar with our collections, and this one in particular, this is going to look super weird. You're going to be like, is this really the data? Are you sure? But for us, it makes writing algorithms easier. And we think that in the long term, potentially, it makes it easier for you too, because you never have to worry, is there a time dimension? Because you know what? There is. There will always be a time dimension. Okay. So this is an example of one of our Zarr stores. The data has been consolidated across all granules. That's why you have 196,000 time slices there. We have standardized on latitude, longitude, and time, so there can be absolutely no confusion as to what these coordinates are. We have bounds for them. And then we have this single data parameter, in this case, the snow precipitation rate. And then at the top level, we have some metadata that allows you to tie this Zarr store back with the original source data product, including some documentation with that DOI. All right, chunking. Some people love chunking, willing to talk about it for a long time. Some people have no idea what chunking is. If you love chunking, all I really want to say about it is that we had to pick something, and we picked sort of compromise chunking. So no matter what algorithm you're doing, the access pattern, you should get reasonable performance. That's what we're doing. And if you don't know what chunking is and you don't really care what chunking is, I just want you to know that we've picked a chunking pattern that should work reasonably well, regardless of how you are accessing the data. All right, so now I'm going to do a demo. All right, so I will do that, thank you. All right, can you read that? How do I do that? It does not want to. All right, I feel like I should know this. Does anybody know how to collapse this? Oh, okay, thank you. There as well. All right, thank you. All right, so I'm going to give you a demo of how to look at the water cycle in California's Central Valley. I am not a hydrologist. I worked with some of the hydrologists at the GeoSDISC in order to develop this tutorial. But the basic idea is quite simple, even for those of us who are not earth scientists. If you read the news, you know that in California, snow is really important. So over the winter, snow falls in the mountains. In the summer, the sun comes out, it melts that snow, runs down into the valley, and we hydrate the valley. So very sort of simple sort of principle going on here. So we will, import a lot of I'm sure these libraries look very familiar. Okay, so our first step here, we're going to check to make sure that this notebook is running in US West 2. As a sort of a policy decision, NASA makes direct S3 access to our data only available from US West 2. So if you want to access these Zarr stores, you will need to actually be in AWS. All right, and then I have some information about this GLDAS product, a link to the product description. Again, it's global coverage, quarter degree, 3 hourly. And then the two variables we're going to look at are a snow precipitation rate variable and a soil moisture variable between 10 and 40 centimeters deep. Then we're going to pick a location. So the blue box is over the mountains in California. That's where we're going to look at the snowfall. And then the red box is over California's northern Central Valley. Date range. So there was a drought in California from 1987 to 1992. So we're going to look at the snowfall and soil moisture in 1992 during the end of that drought into 1993, which was when the drought ended. All right, so the first thing we need to do is look at, call the Common Metadata Repository, which is our centralized place for metadata to find the data. This is a little clunky, so if you do this, I suggest just like copying and pasting these functions. Then once we have that information, we're gonna actually load the data set into Xarray. So here we've opened the two variables. The first is that snow precipitation rate. The second one is soil moisture. And then we're going to create a function to calculate the area average time series so that we can see what the snow looks like over time. And because looking at the snow at a 3-hourly temporal resolution is a little hard to see, we're going to actually accumulate it over the entire month. All right, and so here, this plot where I pulled the data and ran that algorithm, the area average, and aggregated all of that, took less than 2 seconds. And we can see that the 1992 winter, we didn't get much snow. 1993, we did get snow. So, all right, what we were expecting to see from that drought information. So then we're going to look at the soil moisture of the valley. And what we're going to expect to see is that in that year where we had a nice snowpack, the soil is going to dry out more slowly over the summer. And we're actually going to use that higher temporal resolution to be able to see when that happened. So here we ran that calculation. This time around it took less than a second to run. And in 1992, when we didn't have a lot of snow, the soil moisture gets below 20% in mid-June. But in 1993, when we got more snow, the soil stays moist for longer and we don't fall below that 20% until July. All right, so I just wanted to say that for our on-premises system, it would have taken about 40 seconds to run that calculation that took about a second. So this is really much faster, even for us. All right, so documentation. This link has a how-to, including how to search for that data and load it. Some limitations. In order to do this, you will get AWS credentials. They will expire after an hour. If you go to lunch and you come back, your Zarr store will suddenly no longer load. It's okay, get new credentials, you'll be fine. You must be in US West 2, as I mentioned. The data discovery is a little clunky. We're working on getting that metadata into our metadata repository in a little nicer fashion. We're anticipating that the metadata is maybe not going to fulfill all your needs. We don't know what tools everybody is using, so we would love it if you could tell us like where things aren't working. The dimensions for these need to be rechunked because right now they load somewhat slowly in Xarray. Our time dimension has fill values, which didn't seem like a problem to us, but does seem like a problem to some libraries. So we're working on it, but you may need to mask those before you start plotting. And then some future plans. Like I said, we want to improve the chunking of the dimensions to make loading faster. We want to make more data public, including those changing data sets. We have some ideas about how we're going to do that. We want to improve the metadata, improve discoverability so that you can find these things more easily, deal with the fill values and the dimensions, incorporate community feedback, including all of yours, into making these Zarr stores more usable. And this is how to do it. We have an email address for you. This will go to our help desk. Our help desk is a human being, actually several human beings. They will make sure that your question gets answered and gets sent to us if necessary. And I just wanted to acknowledge the entire GESDIS team. This was definitely a group effort. OpenScapes, which is a lovely organization helping people move their algorithms into the cloud. I was running on their Jupyter Hub. I want to thank Luis Lopez, who's actually in the audience here, for helping with the tutorial. Thank you. The ESDIS search and discovery team for helping with the metadata, and then all these lovely folks who put free public imagery out there. And that is all I have.
Thank you so much. Okay, we're going to open it up for questions. And as a reminder, if you want to submit a question remotely, you can do so on our Slack channel for the Earth Ocean track. So are there any audience questions? Okay.
Hello, awesome talk. I also work with Zarr data, and I'm wondering, I have two questions. I was wondering about the sort of uniformity of the Zarr store you showed. Was that due to the pre-regridding before putting into Zarr, or?
Okay, so Giovanni has historically worked with regularly gridded data. We have at NASA, nobody else uses this terminology, but we have something called level 2 data, which is in the frame of reference of the satellite. And then we have level 3 data, which is where they've put it on that regular, in this case, global grid. In this case, it's actually not even direct satellite data, it's model data, so it was just in that regular latitude and longitude grid.
I see. And my other question is, what sort of compromises did you maybe come to when you were choosing your chunking scheme?
Okay, so in a certain sense, you can look at the data as we bring it into the archive as that pancake chunking, because we have just one time slice in every single file. So if you want to do a time series, you have to open every single file and get a point out of this file. You could alternatively go the churros route and have, all the data at one location in a single chunk. And that's great for time series, but then if you want to do a map, again, you have to open all the churros in order to get that map. So what we've done is chunked things so that there are usually several hundred time slices in there, and a portion of the globe. So if you get a map, you don't have to open all of the chunks, and if you get a time series, you don't have to open all the chunks.
Thank you.
Any other questions from the audience?
Thanks for the presentation. So my question is related to Parquet format. So you mentioned about that it's hard to update if the data get larger. So recently there is spatial extension, and people are I saw lots of communication going on GeoParquet file format. So what about that? Is it relatively solving in?
You are asking me beyond my knowledge. So we were doing this back in 2018, 2019, 2020. I would say that just in general, the way S3 works, as far as I know, still, is that you have to write an entire object. You can't write a partial object. And so just the network traffic, if you're trying to update something that's, a couple terabytes in size, is not great.
Thanks.
Okay, and then it looks like we have one question coming in on our Slack. So Martin Yo says, what do you think you will do to deal with the fill values? They are valuable information to some users.
Okay, so right now we have fill values in a time dimension and in the data array itself. We will leave the fill values in the data array. So we're not going to make up data where we didn't have data before. The question is what to do with the time dimension. We can, because this is regularly gridded data, we actually this is model data, but we also have satellite data. If for some reason there weren't retrievals from that day, and so there is no granule for that data, we can still have a time value for that day in the data, or that hour, or whatever it is, and then just leave it as fill values in the data array. So that's the current plan. That's what we're currently thinking.
I was just curious if you're showing, bringing this stuff to the cloud and making it cloud-enabled using Zarr. Is this a trend for other NASA distributed archive centers? Or, I don't know, you probably can't speak for all 12 centers.
No, I can't. Right. So NASA is making a big push to get all or most of its data into the cloud. And it is asking people to access it from there so that you can have your compute right next to the data. And if I recall correctly, in Earth Data Search, there is an ability for you to check a box that will let you just find the data sets that are currently in S3 and available right now.
So I know you mentioned you can only access it in US West 2. Is that to avoid egress charges then?
That is all about egress charges, yes. There has been some discussion about letting people pay for the egress themselves if they would like to access it somewhere other than US West 2. And if you are interested in that, I would love to get official communication to that effect to forward to the powers that be.
Awesome. And then another question. So I know you had mentioned you sort of scrolled past the part of the notebook where it was sort of searching and looking for the data. I know that you mentioned that you're looking into using it with the Earth data search and that, or the existing search interface. Have there been discussion about using some of these other alternatives like the spatio-temporal asset catalog stack to be able to search?
Yes. So it's not terribly well advertised, but the Common Metadata Repository does have a stack endpoint, so you can actually get stack from it. However, I'm not sure if you can get these Zarr stores out of that endpoint because it was oriented toward granules. But yes, we do actually have stack, and we've had some discussions about Zarr and stack.
Can you expand on your strategies you're considering for continuously updating Zarr stores?
So our current thought, there are a number of sort of players out there at the moment. We're currently looking into LakeFS, which will allow us to version the data sets. The idea being that when you come and you open a data set, you will get a particular version, and we can go ahead and update and create a new version as the new data comes in. We don't want to have too many versions lying around, and we've done some tests, but we haven't it's not production hardened. So there's still some work to do in that area. We've also looked at Array Lake. We've looked at some other places. It's an evolving field at the moment.
Any other questions? Okay. Thank you so much, Dr. Smit.
Thank you.